They'll be, we got all out of the medal. Well, good afternoon, everybody. This meeting is taking place via a webinar. If you are staring at a screen at the moment, apart from doing your personal emails, if you're staring at a screen, if you look at the top left of your screen, you should see a small green shield. If you look at the top left of your screen, you'll see a small green shield. That symbol means that you're collecting stamps. No, sorry. That symbol means that you're using the most up-to-date version of Zoom and that it is secure. Questions can be asked at the end of the lectures, but as you will be muted, please use the chat facility found at the bottom of your screen. Your questions will only go to the panelists and they will be read out by the RAS Deputy Director, Dr. Robert Massey. Now, I have to remind you of important deadlines. First one is for the RAS prizes for the best PhD theses in astronomy, geophysics, and instrumentation that have been submitted in 2022. These are prizes for the best theses in astronomy, astrophysics, the Michael Princeton Prize, and the Solar System Sciences and Geophysics, the Keith Runcorn Prize, and the Instrumentation Prize, Patricia Tompkins Prize. The closing date for nominations for these awards, which carry a cash prize of £1,000 each, and with the opportunity to make a presentation at a future ordinary meeting of the RAS, is the 21st of January. So please, either your own students or encourage members in your department to submit names of students. Second is the RAS GCSE poster competition. And more information about that can be found on the RAS website. The deadline in that case is a little later on, it's February the 14th. If you're thinking of applying for an RAS grant at all, as you know, we do give small grants for all sorts of things. The deadline for that current round is on February the 20th. We'd also encourage people to make application for suggestions for the specialist discussion meetings in the next academic year, 2023 to 24. Suggestions are invited from fellows who wish to propose specialist discussion meetings for the academic year beginning October 2023. See the website, yet again, for further information, and the deadline is the 3rd of March, 2023. I'd next like to note and congratulate some fellows of the Society and a friend of the Society as well, who have been mentioned in the New Year's Honours List. And that is Professor Julian Wright, who is awarded an OBE, Dr. Brian May, who becomes a Knight of the Realm, a KBE, Libby Jackson, who becomes a CBE, and Professor Terry Moore, who becomes an OBE. Congratulations from the Society for those 4 people. Now, I now have to read out, I hope it's not a too tedious list, I'll do it as quickly as I can, but it's our 2023 RAS Awards list. I'm pleased to announce the following recipients of the Society's awards in 2023. Honorary Fellowship to Dr. Rita Samburana of NASA Goddard Space Flight Center. Honorary Fellowship to Professor Eric Perg of the Niels Bohr Institute in Copenhagen. Honorary Fellowship for Dr. Pramana Pramadi from Boscha Observatory, the Institute of Technology, Bandung. The James Dungy Lecture is awarded to Professor Marina Garland at Imperial College London. The George Darwin Lectureship to Dr. Dominic Bowman of the Institute of Astronomy at KU Leuven. The Group Award is to the Meerkat, I suppose it should be Meerkat team. The Winston Award Geophysics is to Dr. Ravindra Desai of Imperial College London. The Winston Award Astronomy is to Dr. Alexandra Ammon of the Cavalier Institute in Cambridge. The Fowler Award Geophysics is to Dr. Oliver Allenson at the University of Exeter. The Fowler Award in Astronomy is to Dr. Christopher Berry at the Institute for Gravitational Research at the University of Glasgow. And a service award in astronomy is to Mr. Charles Barclay, formerly of Marlborough College. I think he's here today. Well done, Charlie. The Agnes Mary Clark Medal is to Professor James A. Bennett, formerly of Oxford. The RAS Higher Education Award is to Dr. Ravindra T. Desai at Imperial College London. Secondary Award, that's secondary education, rather than secondary award. Secondary Education Award is to Dr. David Boyce at Uppingham School. The Primary Award to Ms. Inga Heimecker at Europa School, UK. The Annie Maunder Medal is to the Black in Astro Consortium. The Jackson Gwilt Medal is to Professor Roberta Abraham and Professor Peter von Dockum, respectively, the University of Toronto and Yale. The Price Medal will be presented to Professor Rhian Jones of the University of Manchester. The Chapman Medal to Professor Nicholas Achilleos, Achilleos at University College London. The Eddington Medal is to Dr. Monika Mosiborowska, I think, at Rabaud University. And the Herschel Medal is also to Rabaud University, Professor Heino Feiker. And which brings us to the 2 main awards of the year, which are the gold medals. The gold medal for geophysics is presented to Timothy N. Palmer of the University of Oxford, and the gold astronomy medal is presented to Professor John Peacock of the Royal Observatory, Edinburgh. Right, we'll move on to the program now, and it's my very great pleasure to introduce a speaker following on from the Group A award last year. I hope I get this right, Professor Joop Schaye from the University of Leiden. About right? Okay. Who's going to talk about cosmological simulations of galaxy formation. Joop Schaye, after obtaining his PhD from Cambridge University, spent 4 years at the Institute of Advanced Study in Princeton as a long-time member before taking up a faculty position at Leiden University in 2006. He stayed there, and since 2011, he's been a full professor. Schaye works on the simulation and observation of galaxies, the intergalactic medium, and large-scale structure. He has led influential international simulation projects, including OWLS and EAGLE. In addition, he has developed analytic theories and has led observational campaigns to study the connection between galaxies and the gas around them. Thank you very much. This microphone?
Yeah, this microphone and the control unit.
This is a pointer.
All right, thank you very much. It's an honor to be here. So I'll tell you something about cosmological simulations of galaxy formation. I'll say a little bit about what we did, that we got the award for, and also then I'll say something about where I think this field is going. Here's some pictures of a simulation of galaxy formation, where on the top, what we see there is time going from left to right. This is the battery, I think. From left to right, you see the cosmic web developing, structure developing. And if you zoom in into individual pixels, basically, in this top panel, you would see simulated galaxies like the one below. So these galaxies form naturally in these simulations. We don't have to do very much. Nature just likes to form these apparently, and so does the computer if you put in the forces of nature. So what are cosmological simulations and why do we do them? Well, what I mean by cosmological simulations is hydrodynamical simulations, that includes gravity as well as gas, of a representative part of the universe. So not just zooming in onto one object, but large enough volume to have a population of objects. And they are useful for studying galaxies themselves, formation and evolution of them, but also for cosmology. You want to measure the cosmological parameters by, for example, comparing the growth of structure, then you will need to have some model to compare to. And what the baryons are doing is important these days, because we're going to quite small scales with observational surveys. And there the baryons do not trace the dark matter fully, so we need to understand that. What goes into these things? Well, we take a cubic region of the universe with periodic boundary conditions just to avoid edge effects. If it's really a representative volume, then that is okay. And then this box does not expand. We just take out the expansion as a coordinate transformation, which is a solution to the Friedmann equation. And that's where dark energy comes into play, for example. So there's no dark energy fluid in these kinds of simulations for the most part, unless it's an interacting dark energy. Then it's a simulation, so you have to discretize. We always discretize time, but then you can choose whether you discretize the mass in the universe or space. In the simulations that I'll show, we discretize the mass. Then we put in dark matter. Simplest simulations like EAGLE is just cold dark matter. And also ordinary matter, which is the baryon matter. Then we have to have initial conditions. These days, they are fairly well known from the cosmic microwave background radiation and also from observations of large-scale structure. But of course, the uncertainty in those initial conditions is still very much of interest if you want to do these simulations for cosmology. If you want to do them for galaxy formation, they're pretty well constrained for that purpose. We cannot simulate everything directly because the range of scales, as I'll show next, is too large. We need some prescription for what happens below the resolution. And we call those subgrid prescriptions. And to see why these are needed, to appreciate that they will always be needed, here's just a range of skills that is relevant for these kind of models. For the cosmological simulations, we want to do ideally the entire observable universe, several gigaparsecs. But even if we don't do such a large volume, we want to study clusters of galaxies, and maybe even the star clusters in them. But that's not all the skills that matter. These are the objects we want to study. To do that, we need to follow the formation of stars, stellar evolution. In fact, we even need to care about the atomic scales, because the collisions between atoms is what causes radiation. And the radiation is what we see, and the emission of radiation allows the gas to lose its binding energy. Actually, we even need to care about what happens in stars, because there's nucleosynthesis inside the stars, the interparticle distance inside the stars, and these produce chemical elements that are later released and observed. So clearly, 36 orders of magnitude is too much. So we need to draw the line somewhere, and then we switch from direct simulation to subgrid models. And where exactly you draw that line depends on your interest. If you're interested in large-scale structure, you invest more of your resources in going to a larger volume, and you need to go to subgrid scales, maybe already on the galaxy scale. If you're interested in the formation of dwarf galaxies, obviously you would invest your resources to do a smaller volume, but then you go to smaller scales and probably resolve it in star clusters. Still do this, okay? So here are some examples of the subgrid models that are typically needed. I put them in 3 categories: microscopic processes, things to do with stars, and things to do with black holes. So the microscopic processes, you should think about how much radiation is emitted by a gas as a function of its chemical composition, density, temperature, and maybe the radiation field that it's impinging on. But also the formation and evolution of dust grains, which matters for the light that is emitted, but also, for example, for the formation of molecular hydrogen. For stars, we need to know how they form. Once they formed, how they evolve, particularly how much mass they lose, and how much energy they inject, and how much momentum they inject. Black holes, again, the formation, the way they grow by gas accretion, stellar accretion, emerges with other black holes, and also what happens in terms of feedback. Jets that come out of the region near the black holes, and winds that are blown from accretion disks. Something else is, I'll just put that in because I'll show this, is often appreciated, but the movement of the black holes also needs to be done with subgrid models. They're supposed to be more massive than the dark matter particles, for example, much more massive, and that's why they would have dynamical friction. They would experience dynamical friction. In a simulation, these black hole particles tend to be only a little bit more massive, or even similar mass to the particles that represent the dark matter, so we wouldn't have this dynamical friction. And we need some prescription for that, which actually is very important. The most important thing, however, is these feedback processes. So going back before this Eagle project, and years before that, there was always a big problem. And when people did hydrodynamical simulations, they didn't really get galaxies out that looked the way I showed you on the first slide. The galaxies that came out were basically all bulgy. They formed their stars too early, and they were too massive. That got resolved, and it got resolved for a number of reasons. The most important reason was that the subgrid descriptions for feedback were improved. In particular, they were changed to overcome what we call numerical overcooling. What does that mean? It means that the gas is radiating away too much of its energy. So when feedback happens, when energy from supernova is injected in the interstellar medium, it's injected in too much mass because of the poor resolution, which means that the temperature doesn't go up very much. If the temperature doesn't go up very much, then the cooling time is short, and the gas emits its energy in the form of radiation instead of expanding through shock waves. So you need to overcome that. And you need to do that with some trick. And when you have this trick, you need to calibrate the trick, because we then don't know a priori what the right answer is. We need calibration models. And that is something else that was realized. And the other important thing is, what do you calibrate into? And the realization that you need to calibrate into something that depends on what the question you're asking is also important. So for the cosmological simulation of galaxy formation, for example, it's the mass function of galaxies, how massive they are. And finally, it was realized that we need not just stellar feedback, but also active galactic nuclei feedback from growing black holes. And that's really important for the most massive galaxies. Here's some examples, some pretty pictures. Here's a picture of the Eagle simulation, but there's other groups that do very similar simulations. There's the illustrious TNG collaboration, there's the Horizon collaboration, and there's more of these things. And they're quite comparable, these simulations. Eagle is really a teamwork, so this is a team award, and I want to list all the people that contributed to this this project. Actually, in fact, there's many more than this. The the simulations have been analyzed in hundreds of papers because all the data has been publicly released. But these were the core developers that shared the prize. And I want to particularly highlight Richard Bauer. As you may have heard, unfortunately, a week ago, Richard passed away, Professor Richard Bauer, after a struggle with cancer. And Richard is there in the third place on this list of authors because he was one of the most important people in this collaboration. He really did some key work that I'll try to highlight as well. Next, what I'll show you is a video. This is a video of a small fraction of the Eagle volume, because if I show the full volume, then you don't see very much. It's 25 megaparsec on a side. It will rotate and we go forward in time. The color coding is the temperature of the gas and the intensity is the density of the gas. What you can see here is the development of this cosmic web. So on the bottom left, you can see redshift going down and the age of the universe going up. And if you look carefully, then what you see is what looks like explosions. They'll see here on the left, for example, you see one. And that's the winds driven by star formation and in the largest explosions by active galactic nuclei. You can see they blow these shells into the intergalactic medium. The galaxies themselves are too small to see in this scale. They're basically 1 pixel. And here, after redshift 1, not that much happens anymore. Again, the expansion of the universe has been scaled out. We're looking in co-moving coordinates. And this hot gas, these hot bubbles, it's heated mostly by active galactic nuclei, but also just by shock heating from gravitational inflow. So these simulations were calibrated to reproduce the galaxy mass function at redshift 0. And that's what is shown here. So this is the number of galaxies per unit volume on the y-axis as a function of the mass in stars on the x-axis. And you can see these are actually, the Eagle consists of multiple simulations at different resolutions, different box sizes. That's why there's multiple curves here. And you can see that works well. And once you do that, you can also reproduce, and this wasn't calibrated, the mass function at different redshifts. The light blue line is always the same. For reference, it's the redshift 0, 1. And then you can see here at redshift 7 and 3 and all the other redshifts, the agreement is also quite good. However, the mass function, it turned out it wasn't sufficient. Here's an example of one galaxy in 4 different simulations that all reproduce the galaxy mass function. But you can see that they look actually different. Particularly these 3 here are quite centrally concentrated. This one is much more diffuse. Indeed, if you look at the statistics of the entire simulation, you plot the size of the galaxies, their half mass radius versus mass on the x-axis, and you can see that 3 of these 4 simulations have this dip at about 10 to the 10 solar masses. Right? And that dip here is basically because of this numerical overcooling that we couldn't overcome in these first simulations at this mass scale. It still was okay for the mass function, but the sizes really were a problem. So we needed to calibrate also to these sizes to get reasonable results. And once we did that, everything else followed, and actually many other things agreed very well with observations. And Richard Bauer is actually the person who came up with the trick we used to compensate for this numerical overcooling. So that was absolutely critical for this project. I just want to give a few examples to give you a little bit of a view under the hood of things that people usually don't talk about, but that are also very uncertain. There's a lot of uncertainties in these simulations, even after calibration. So here's an example of the black hole mass, the central black hole mass versus the galaxy mass, where the red line is our fiducial model. And this yellow line, where the black holes don't grow at all, that's what happens if we do not do this trick that I told you about in the beginning, where we move the black holes by hand. The trick is to move them at every time step down the potential gradient so that they end up in the centers of galaxies. We're supposed to do this naturally by dynamical friction and stay there, but we don't resolve the dynamical friction. So you can see that this trick is absolutely essential, otherwise the black holes wouldn't grow at all. And what we do is probably too strong. Dynamical friction wouldn't be that effective. So this is a significant uncertainty. I told you these simulations have to be calibrated. The feedback has to be calibrated in the subgrid models. That doesn't just mean how much energy should you inject. And that's what people usually talk about. But here's an example of what else matters. For example, here's a side view, an adjoint view of a galaxy. Several different versions of the same galaxy. And what is shown here is the winds that come out of these galaxies. The winds, they tend to propagate in the path of least resistance, so perpendicular to the disk. All of these simulations inject the same amount of energy per unit star formation. But you can see on the right, the winds are much better developed than on the left. And all that is changed is how is the energy distributed around this supernovae? Is the energy injected in low density gas or in higher density gas? Mass weighted or isotropic, different things like that. And if we put it in higher density gas, then more of it is radiated away. The structure of the interstellar medium is not very well resolved, so we need to make some assumptions here. And you can see that these matter as much as changing the amount of energy by factors of a few. So calibration is not just about picking numbers, it's also how you implement things. So these simulations, and also the ones by other groups, have been extremely successful in the sense that they reproduce many observables that they weren't tuned and can be used to make mock observations to help interpret observations. But they have some big uncertainties, as I already told you, but they also have some other drawbacks. For example, the volumes are too small to study large-scale structure. Eagle had a 100 megaparsec box. It's too small. We have massive galaxies of high redshifts or clusters at low redshift. A very important drawback is that the interstellar medium is not allowed to cool below 10 to the 4 Kelvin. So there's no cold molecular phase in any of these simulations. That means the interstellar medium will not be very clumpy. That affects the way galactic winds develop, like it affects the thickness of the disk. It has lots of problems. Another issue is that because dark matter particles are massive, there's not that many of them. One dark matter particle may represent a million solar masses of dark matter. You get collisional effects that shouldn't be there. It should be almost like a collisional fluid. And that heats up the stars in the galaxy, changes the morphologies of the galaxies, make them too thick and too large. So the next generation of simulations that we are doing, and also other people are trying to address these problems too, will overcome some of these problems, at least to some extent. Two projects that we're working on are FLAMINGO and Colibri. FLAMINGO we're writing the first papers on now. Colibri will probably come in the summer. And they both use much larger volumes. And that's mainly just by increased efficiency of algorithms and bigger computers. We added a lot of physics in Colibri so that we could allow the gas to become molecular and cool down. So for that, you need molecular network, chemical network, you need to include shielding of the radiation fields, you need to have dust that forms and evolves and is coupled to the molecular hydrogen. So you need a lot more physics. And to overcome the spurious heating by dark matter particles, we just use many more dark matter particles relative to the number of baryonic particles than were used in the past. Here's just some illustration for a small test simulation of Colibri to bring home this point of the cold phase. So here's a small volume of a simple simulation where we plot temperature versus gas. And these are just the mass elements in a simulation. And this entire region, we do not allow to be populated in Eagle, and the same is true for simulations by other groups. Whereas in Colibri, these newer simulations, we do allow this gas to cool down. And the color coding here is a neutral hydrogen fraction. You can see here it's ionized, here it's neutral and yellow, and here on the bottom right, it's molecular. And that allows us to form, for example, much thinner disks, you can see here. FLAMINGO is the next big project that we're now, as I said, writing papers on. This is meant for comparisons with cosmological observations, so it's very large volumes. It includes the largest hydrodynamical simulation ever done, with almost 1 trillion particles. So here's, to put this in perspective, the Eagle volume, 100 megaparsec at a site, and this picture is something that Richard Bauer contributed to. It wouldn't have looked anywhere near as pretty without him. Now we shrink this to this size, and this is then the Eagle volume. You can see it's much, much bigger, but thanks to the big computing power that we have these days, we still have enough resolution to see a lot of detail. We track, in this case, not just the gas, the cold dark matter, and the stars, and this is just a small fraction of the volume, but also neutrinos. We have a new treatment of neutrino particles from Willem Albers. We can see that the neutrinos are also clustered, but because of free streaming, they're not as clustered as the rest of the matter. Another new thing that we've done, which is also inspired by Richard Bauer, because he's applied this many years before to semi-analytic models and persuaded us all to apply the same techniques to hydrodynamical simulations. The other technique is to use machine learning for the calibration. Whereas in Eagle, we did all of this by hand. Here, what we did is we built emulators using Latin hypercubes, grids of small simulations that we could interpolate. And here's an example where we use this emulator to predict what happens if you change this one parameter in the subgrid model for AGN feedback, how hot you make the gas. And you can see the effect on the galaxy mass function here on the left, and the effect on the amount of gas in clusters of galaxies. And these are the two observables that we calibrate these large-scale structure simulations to. So then we have many other parameters, we have 3 other parameters that we emulate, and then we can fit to the set of observables. The white region is a region that we can resolve in the volume that we have. And you can see we can then reproduce this mass function and the cluster gas fractions. And these calibrations are then applied to much larger volumes. We also produce light cones on the fly. So the past light cone of a few observers that we place in the box, and then we can make, for example, Sunyaev-Zeldovich observations, all sky, weak lensing, X-ray. And here's just one example. This is the cosmic microwave background lensing map signal there, which may look like noise to you, but if you compute the power spectrum, you can see that the power spectrum is a function of the multipole number here, where large scales are on the left and small scales on the right, reproduces the data very well. And now we can do similar things for these other gas observables and do the cross correlations between them as well, for example. Okay, I'll finish with this slide, and then hopefully have some time for questions still. So here's some takeaway messages. Cosmological simulations have come a long way. They're now sufficiently realistic to use, to compare to observations, both to test the theories and also to figure out what kind of artifacts might also be present in real data, for example, selection effects, things that come out of biases that might be introduced by the way the data is analyzed. You can also use them to design new campaigns for observing, to write your observing proposal or your instrument proposals. However, galaxy formation is not a fundamental physical theory. There's a lot of uncertainty in there under the hood, and there's some calibration that is needed. So in terms of ab initio predictions, how many galaxies are there of certain mass, they're not very good. So in that sense, they're better for testing scenarios than for quantitative predictions. There are exceptions. There's some things that you really can do quantitatively. Not everything is uncertain, particularly when it comes to the lower density gas, we can do much better. They do then require a calibration of these subgrid processes. And that is not just tuning of free parameters, it's also choices you make, how you implement things. The next generation of simulation is coming up from us and others. They will compare to Eagle and models like it. There will be bigger volumes, many more resolution elements, more physics. The main jump, I think, for the simulations of populations of galaxies is that there will be a cold interstellar gas phase, which allows for much more realistic modeling. And also, machine learning will play a role. So the simulations will be used to train emulators, which are not just used for calibration as we've done, but can also be used to make predictions and to investigate, for example, the interactions between cosmological parameter changes and physics changes. Thank you.
Thank you very much. Very interesting. And thank you too for your informing us of Richard Bauer, which I personally hadn't been aware of. I'm really sorry to hear his passing. Can I throw it open to questions on the... Please give your name for recording purposes. Thank you.
Garth Barber. Do you see with the FLAMINGO simulations any problem reconciling it with the very ultra ultra high Z JWST observations?
Do we see in FLAMINGO a problem with the JWST observations? The resolution of those simulations is a little bit too low, I think, to make good predictions for what happens at high redshift. We can see if we look at the history of the galaxies that we can do the low redshift part, but at high redshift we really lack the resolution. We do have the volume, but we still lack the resolution.
Other questions? Yes, Michael Robinson.
Michael Robinson, could you say a little bit more about the distinction between what you call calibration and the tuning of free parameters? Because it did look a bit like, you know, something didn't fit very well, so you tweaked something to bring it into line.
Yeah, I mean, these are just different words for the same thing. So you have to choose an observable that you calibrate the uncertain feedback properties to. And which observable depends on what you want to do. If you want to do reionization simulations, which I didn't talk about, but we do them also, and for example, you would tune the escape fraction because you can't simulate that to get a reionization redshift that agrees with observations because you can't predict that. In our case, we were interested in the galaxies, so we want to get the galaxy halo connection right, so we calibrate to the galaxy mass function. As I showed, that wasn't enough, so we needed one more observable. Hopefully, you don't need even more, but depends on the problem, you might need more, which then limits the kind of questions you can ask of those simulations. The point I also made is that calibration is not just in changing a free parameter, sometimes a free function instead, or just a choice of implementation.
Anything online? Can we have one from online?
Got one, assuming is this working? Good, okay. We've got one from Ofer Lahav. What is the status of incorporating neutrinos in your simulations?
So status is good. So for a long time, people did it mostly by changing the initial conditions and not really having neutrino particles, because neutrino particles introduce a lot of Poisson noise. But there's now new techniques developed to suppress that Poisson noise. And one of them is what we're using here. It's called the delta F method for the aficionados. Willem Elbers, a PhD student in Durham, has nice papers about that. There's other groups that do similar things. So in FLAMINGO, we can include them with the suppressed noise at little extra cost.
Hello, Paul Wheat. I'm just wondering what assumptions you make about angular momentum, whether it's randomly distributed throughout the universe and whether there's a net zero overall.
Net zero on the scale of the entire universe, you mean? Well, we certainly assume that's the case. Whether or not that's true is not something we can answer with these kind of simulations because we assume. But yeah, if there was some global asymmetry, anisotropy of the scale of the entire universe, we would have to put it in. Yeah.
Richard.
Richard Ellis, it's been suggested that cosmic rays should be incorporated in many of these simulations. What's the status on that?
Yeah, there are physical pieces of physics that are not in Eagle and also will not be in our next generation simulations that might well be important. And one of them is cosmic ray pressure, indeed. The problem with cosmic rays is that it's still very unclear whether it's either very important or not important at all. It depends on the microphysics. So there's very important and useful work being done to test this. But at the moment, our feeling was that if we do one big investment of computational time, it's too uncertain to pick one of those scenarios. But I wouldn't be surprised if it indeed turns out to be important.
Any more online yet? Okay, front here. Wait for the.
James Salmon, if you run the simulations forward, what do you get?
Beyond present time.
Yeah.
We've actually done that with Eagle. Yeah, there's papers from Jaime Salcido and David Barnes where we did that. And we did this mainly because we were interested in the anthropic principle and seeing, well, it's a bit too long story for now, but the interesting thing is what we found is that, for example, the cosmic star formation history is now going down, the star formation rate per unit volume, If you wait long enough, it would go back up according to these models, unless you have very strong AGN feedback. And that is because in clusters of galaxies where the cooling time is long, at some point the age of the universe is similar to that cooling time, and you start forming you start cooling down that gas. But if you have very efficient AGN feedback, you can prevent that.
Any further questions? Can I ask what's a very naive question?
Those are the best.
Which, looking at all these wonderful simulations, I mean, the beautiful graphics and whatever, do you have a feel yet as to how unique you can say about galaxy formation? In other words, these are the very important things that you need to put in. All these other things are peripheral. These are the major, just 5, 6, I don't know, particular major processes that do it all, and you can forget the rest. Have you reached that stage yet or not?
Not fully, but it really depends on the questions you're asking. To give you an example, if you're just interested in how many stars are forming, you don't actually have to care about the star formation law. If you're interested, however, in how much gas there is in the galaxies, then the star formation laws are really important. But I think there's disagreement exactly about which physics is important, but what some things people agree on. I think everyone agrees that you need more than one channel of feedback. You need something that dominates at low mass and something else that dominates at high mass galaxies. So for example, black holes and supernovae. But
Okay.
it's not unique.
Okay, well, thank you very much. Congratulations on getting a FLAMINGO as an acronym. My next one's going to be DODO.
Albatross is my favorite.
Albatross. Okay, thank you very much. For our next talk, which is the George Darwin lecture, I'm absolutely delighted to introduce Alan Fitzsimmons from Queen's University, Belfast, who's going to talk about small body impacts across the galaxy. Now, Alan is Professor of Astronomy at the Astrophysics Research Centre at Queen's University, Belfast, in the United Kingdom. He performs observational studies of comets and asteroids, mostly in our own solar system, and he's the author of over 160 scientific papers. Highlights of his career include studies of the collision of comet Schumacher-Lovell 9 with Jupiter, which I'm sure many of you remember, and an interesting one, the 2008 TC3 identified as the first asteroid predicted to impact Earth. I asked him about this rather worriedly. He said, yes, it had hit Earth, it's not one to come. It hit apparently somewhere in the Sudan, but it was only about 3 or 4 meters in diameter, so it didn't do, fortunately, a great deal of damage. And he's also been involved in some of the discoveries of the first interstellar objects. Currently, he's an active member of the Asteroid Terrestrial Impact Last Alert System, ATLAS. The word last alert rather worries me there. And the NASA DART and ESA HERA planetary defense missions, obviously of particular current recent interest. And he asked me to point out that neither asteroid 4985 Fitzsimmons nor comet C2018X2 Fitzsimmons are expected to hit the Earth in the next few millennia. So with that good news, I hand over to Alan.
Thank you, Carol. And thank you, Mike, for the introduction. I'll just point out that reason I think that asteroid and that comet isn't going to hit the Earth is because I did the calculations, so who knows? Anyway, so yes, I'd like to though start by thanking the Society for my for the award of this lectureship this year. It's really nice to be able to give a lecture like this because I expected to be told, okay, this is what's in your biography, this is what we want you to talk about. And now you're given free rein. So I'm going to really enjoy talking about things I know nothing about this afternoon. Except that I do know something about some of the things, and maybe that's seen in this title slide here. The photographer of which, Professor Simon Green, is in the audience here. Thank you, Simon, for photographing me in front of Meteor Crater. You didn't get my good side because you can see my face. But what I'd like to do is talk about small body impacts, not just locally in our own solar system and indeed on our planet, but further afield. So, let's remember to press this button. So I'm going to talk about impacts on planetary bodies, something of interest to some of us. I'm going to talk about impacts between small bodies. I'm going to talk about impacts when they occur in not just in a solar system such as our own, a medium-age solar system, but impacts in young planetary systems. I'm going to look at what we see in terms of impacts occurring, involving asteroids and comets in old planetary systems. And then, of course, if I could spell it right, I'd like to talk about impactors from other planetary systems. Now, just to go back in time a little bit, of course, this lecture is in honor of Sir George Howard Darwin, who was an incredibly accomplished scientist a little over a century ago. And one of the things he was most famous for was of course, because all great scientists do this, he asked the big questions. And his question was, that's a nice moon, where did it come from? And back then, the leading hypothesis was the lunar fission theory, of course, which he worked on quite a lot during his career, whereby we have a molten spinning proto-Earth, and for reasons which were argued about, a blob detaches itself and forms the moon. And it's interesting, it was interesting to me looking over the history of this subject, that this was still considered a viable hypothesis up until the 60s. And it was only in the 1970s when the first computer simulations showed that another idea could be that the moon was formed by an impact on the proto-Earth by another planetary body, possibly the size of Mars, that thought and that paradigm came to being. And indeed, of course, that's now the leading theory. But I'm not going to talk about large impacts, such as the one that caused our moon. I'm going to talk about smaller ones. And I couldn't really not mention this to start with. I want to talk about natural impacts. But of course, in September last year, we had the first determined impact to actually change the course of the planetary body with the impact of the DART mission onto the 160-meter diameter asteroid Dimorphos. This is the speeded up movie of the last 5 minutes of the life of the DART spacecraft. This jiggling around is actually real. That's the thrusters firing autonomously to make sure it hits this thing dead center, as it pretty much did. And unfortunately, once it does that, you know it's been a success when you only get a bit of the last frame back because it can't send anymore when it's been vaporized. But we know it was also a success because 2 weeks before impact, DART had released the Italian CubeSat Licia Cube. And here we have an image from Licia Cube flying safely past at a distance of 75 kilometers, just a little under 3 minutes after the impact. So here's the parent asteroid Didymos, here's Dimorphos, and one can see this beautiful ejector cone of the material spraying out here. Now, I don't have any references for this because the first papers have only recently been submitted, but look for those in the next couple of months coming out. The important thing about this mission was that it wasn't just our first planetary defense test, our attempt at seeing if we could change the orbital path of a small asteroidal body, but it's also a large collision experiment because the physics involved in predicting what happens in cratering processes and in impacts between objects on a real scale is still relatively uncertain, and this provides us with a very crucial anchor point for simulations. Now let's go to much more smaller, but perhaps more recent impacts even. I don't know if anybody was outside their front door on Monday night, just after 8 o'clock, when over the south of England and heading towards the Midlands, we had a small meteoroid enter the Earth's atmosphere and burn up. Thank heaven for everybody's worry about security and police funding these days, because modern doorbells give these beautiful videos of let me just see if I can play it again, of fireballs occurring. And in fact, if one goes to the UK Meteor Network, one could already pull out the analysis of this fireball on Monday night over the UK, showing both the track it followed over the country and even going back and seeing the orbit that it had around the sun before it entered our atmosphere. Now, fireballs like that are very nice to see. The larger objects, that object was only a few centimeters across. Larger objects are more spectacular, but slightly more worrisome. And of course, this is a dash cam footage of the Chelyabinsk impact from almost 10 years ago. It's hard to believe, where an 18-meter diameter small asteroid entered the Earth's atmosphere, again unannounced, over the Russian city of Chelyabinsk. Now, luckily, the Earth's atmosphere is very protective against small objects like this. Most of the energy was released catastrophically at about 20 to 30 kilometers above the Earth's surface, but the resulting shockwave still injured 1,600 people by collapsing doors and walls and blowing in windows. So it's that kind of thing that you do want to avoid, I would suggest. And that's why, for the past 20 or 30 years or so, NASA has funded a large effort into searching for and cataloguing these small bodies passing near our planet. And just to prove, I don't know what the working practices are of antiquarians over the Christmas holidays, but this is to prove that astrophysicists and geologists certainly never take a holiday. Here's a new near-Earth object discovered on the 27th of December. These are the discovery frames from the Atlas project. This is a relatively large object, 80 meters across, but the minimum orbit intersection distance, the closest it can get to the orbit of the Earth, is about 5 million kilometers. So this passed us safely by. But importantly, down below, we've got a plot of the number of objects discovered each year as a function of time from 1995 up until, well, Christmas. And one can see that due to increases in both detector technology and the simple acreage of telescopes looking for these things, there's been pretty much a continuous increase until last year, when over 3,000 new objects, 3,000 new near-Earth asteroids and comets were discovered. That's over 8 every single 24-hour period on average. And so, as of yesterday, when I checked the catalogue, we had astronomers had identified 31,022 near-Earth asteroids. That'll be apparently, in theory, to 31,030 now. Of which 2,322 are potentially hazardous. They're larger than about 140 meters across, and they pass within 0.05 AU of the Earth's orbit. There's also about 118 near-Earth comets. That's almost definitely an underestimate, because when a comet is relatively inert, we cannot tell the difference between it and an asteroid. So we believe that the number of near-Earth comets is significantly more than this. But that's the total population we've found at the moment. And of course, the important thing about these surveys is that they do two things. They first of all produce this catalogue, which means that you can calculate the orbit, which means you can tell where things are going in the future. And so with detection of the real asteroids, allow us to evaluate that impact risk. Which of these objects are coming close to us? And the date for your diary should be Friday the 13th of April, 2029, when you'll be able to see near-Earth asteroid Apophis at 3rd magnitude as it passes over Western Europe that evening. But another thing that we get out of that is that we can take those observations and model both the size distribution and the orbital distribution of the near-Earth asteroid and near-Earth comet population to determine the long-term, the average impact risks. And so one can see in this plot from Hines et al., published just a couple of years ago, a nice summary of a lot of recent attempts to calculate the cumulative size or size distribution, or rather cumulative luminosity distribution of near-Earth asteroids. We're pretty good down to about magnitude 22, 23, which is going down towards that 100-meter diameter mark. But beyond that, things start getting a bit ropey from the telescopic surveys, simply because of the difficulty of detecting these objects. Now, if one tries to then convert this size distribution into an impact probability, and here we've got the cumulative number of impacts per century, per 100 years, as a function again of absolute magnitude of the asteroid, one can see that when we get down to 18th magnitude, which is of order of 1 kilometer diameter, then we're looking at impact rates of roughly 1 every a few times 10 to the 5 years, going up to one per million years. Whereas we go down to 23rd magnitude, which would be a 100-meter object, we're down at the level of 1 impact perhaps every 10,000 years or so. So the good thing about this is that the near-Earth asteroid surveys tell us not only whether or not something's coming towards us, that particular object you've discovered, but it gives us an overall view of the risk of impact by these bodies. Now, you can also look around you and try to see if those estimates agree with other ways of evaluating this threat of impact. And one way that's been done for several years now has been by observing the moon and looking for impact flashes on the surface of the moon. And there's been some really, really nice work done, and for example, at the NASA and also here in Europe, funded by ESA. And for larger impacts, what one can do is that if one sees an impact flash via high-speed video on the surface of the moon, one can then use spaceborne or telescopic facilities, here in this case, Lunar Reconnaissance Orbiter, and actually identify the impact crater made by that particular impact, for example, here. So this allows an additional check of what, in this case, is generally the impact rate of small objects into the Earth-Moon system. And when one does that, it may, I really do love this plot. This is effectively, again, a plot of the cumulative number of objects colliding with the Earth per year. Against, now we've taken what's been happening, they've taken the magnitude of the object, converted it to a mass or a size, and then with a typical impact velocity of around 17 kilometers per second, you can get an energy in joules, or what's normally done in this work is equivalent of kilotons of TNT. And one can see that if one looks at the telescopic surveys, this is where we have all of these data here. If we look at the lunar meteoroid impact surveys, these are estimates from there here. And this is a log-log plot, and it almost makes you believe in power laws, because one has I mean, there are wiggles in it, okay? Let's not deny that. And some of the transformations from what you actually measure to what you actually want to plot are a little bit uncertain. But one can actually see that there's a pretty good relationship going from the largest impacts that we might want to worry about on Earth all the way down to these small meter-sized, even sometimes centimeter-sized objects coming in and hitting the Earth-Moon system. So that really is quite nice. And I think this plot here is really a testament to all the work done in this field, trying to understand exactly how often do these small bodies hit the Earth and the Moon. As we saw last year, we also now have a good estimate of how often they hit these small bodies hit other planets, in particular Mars. And there's this beautiful observation by the NASA Mars InSight station, the seismometer lander, last year, where they detected actually 2 large seismic events last year, which implied that there'd been a small asteroid impact on the surface of Mars. And then because there's also the Mars Reconnaissance Orbiter that's been up there orbiting the planet now for, I think, of order of 10 years or more, one can go and take a look and indeed identify the new impact that gave rise to that seismic wave traveling through the planet. This impact was, I think, something like 2,000 kilometers from the InSight lander. And so here we can see this 150-meter crater caused by this impact. And so in fact, we now have a very good idea of how often significant cratering events occur on another planet, at least in our solar system, Mars. Now, something that Mike mentioned in his introduction, of course, was for all of us that were around to witness it, the impacts of the 21 fragments of comet Shoemaker-Levy 9 onto Jupiter in July 1994. And the images, particularly from the Hubble Space Telescope, which of course had only been repaired a year beforehand, were nothing short of spectacular. One sees the fireball and then a plume of ejecta coming up from the impact and then falling back down into gravity onto the surface of the planet. And then roughly 30 minutes to an hour later, once that impact site had rotated around from the terminator, one sees the ejecta on the surface of the planet, really covering an area roughly equivalent to the cross-section of the Earth. Really quite spectacular. And the important thing here is that we could actually study these impact processes for the first time, where the impact energies were equivalent to a large asteroid impact on the surface of the Earth. In fact, going up to the KT impact 66 million years ago. And it had very much had a lasting effect that when we looked at both the ejecta in the optical images and in the spectroscopy of the material deposited by those impactors, some of that material was detected many months in Jupiter's atmosphere after the impact. So it gave us a really nice view of what was happening. Now, that impacts onto planets. We have known for over 100 years or so that small bodies in our solar system also hit each other. And this is because back in 1919, Hirayama first looked at the asteroid catalogue as existed back then, just a few hundred asteroids, and noticed that the distribution of orbits were not smooth. Here I've plotted the sign of the orbital inclination of asteroids in the asteroid belt versus their semi-major axis, their orbital distance from the sun. And one can see that this is not a smooth cloud. One has gaps where there are mean motion resonance Jupiter, but within the main bands of the asteroid belt, we can see these density enhancements, which are the asteroid families, where we have had a catastrophic collision between 2 asteroids at some point in the history of the solar system. And we now, instead of having one asteroid there, we have a small family of asteroids, all on a similar orbit. And over time, one moves from a very compact asteroid family in this diagram to one that spreads out through various both gravitational perturbations and thermal effects, such as the Yarkovsky effect. So we've known for about a century that collisions occur between small bodies in our solar system. We also have more recent evidence of how that affects their internal structure. Here's the latest plot of spins of asteroids, and what we have here is spin frequency going up on the y-axis against increasing diameter on the x-axis. I think I'll just change what laser pointer here, if you don't mind. And one can see that for the bulk of asteroids beyond about 200 meters across, there's a very sharp cutoff in rotation frequency, which is equivalent of a spin period of about 2.2 hours. And effectively, this is how fast you can rotate if you're a strengthless body, that you are effectively a rubble pile or a heavily fractured rubble pile with zero tensile strength. If you try spinning any faster, you fly apart due to the centrifugal force. So what you actually see here is, apart from a few large asteroids, the majority of objects that have suffered this collisional history over the history of the solar system, and that's resulted in most of the asteroids, certainly between 200 meters diameter and 10 kilometers across or so, being very heavily fractured and not really solid bodies at all. Something, again, we witnessed in the images from the DART mission just a few months ago. Over the past 10 years or 12, 13 years, we've actually seen this process in action. The first object that was identified as being probably due to an impact between two asteroids was now called 354P Linear, which was discovered in 2010. Later on that year, there was an ejector cloud image that dissipated after a couple of weeks or so around the large main belt asteroid 596 Sheila. A few years later, in 2014, ejector was seen being emitted from another large 100-kilometer size main belt asteroid, Griseldis. And then in 2016, again, a much smaller main belt asteroid was seen actually dissipating due to a collision. And so we've only seen this happen 4 times so far, and we've seen 2 subcritical impacts occur on large asteroids, and we've seen 2 impacts where it looks like a lot of the target asteroid has actually been destroyed in that process. So we're now actually seeing this inter-asteroid collisional evolution in action. And this is coming back to the first slides I showed. This is important because this is how we get our near-Earth asteroids. Because in the asteroid belt, we'll have collisions between asteroids forming asteroid families. When those asteroid families form, immediately you'll have a change in orbital semi-major axis. That can change further for those smaller asteroidal fragments by something called the Yarkovsky effect, which introduces a drifted semi-major axis, and that drift can put them into a mean motion resonance with Jupiter, or a secular resonance with Jupiter and Saturn. And when they're in that resonance, the eccentricity just climbs up, as one can even see perhaps in some of these objects here. And eventually the eccentricity becomes large enough that perihelion there start crossing the orbits of the planets. And that's when we get our near-Earth objects. So collisions on Earth are effectively, at the end of the day, quite often caused by collisions originally in the main asteroid belt. We have another belt of objects out there in the solar system, the Edge-Earth Kuiper belt, or the trans-Neptunian region. Now, there are many more objects in the trans-Neptunian region beyond the planet Neptune than there are in the main asteroid belt, but it's a much larger volume. So the number density is smaller, and of course the impact velocities are slower because of the slower orbital velocities. But there's been some estimates of the collision rates over the past 20 years or so. In fact, pretty much ever since the Edge-Earth Kuiper belt was first discovered. And importantly, there's been a really nice paper recently in the past couple of years doing a very nice detailed calculation of collision rates as a function of distance from the sun, using the known orbital structure of the trans-Neptunian region. And indeed, one finds that, for example, the collision rates are much smaller than the main asteroid belt. For a 50-kilometer diameter object in here, one would only expect something like between 20 and 50 impacts, significant impacts over the history of the solar system. But interestingly enough, that will still generate material from those impacts, ejecta, including dust. And there's been a recent study of interplanetary dust particles and trying to calculate their ages using a new calibration using particle track densities. And what this initial recalibration is implying that perhaps 25% of the interplanetary dust particles that we obtain in the upper atmosphere of the Earth, don't come from the asteroid belt as we, don't come from Jupiter family comets as was originally supposed. They up to 25% may be coming from the trans-Neptunian region. And so we are under, it looks like we may be under a constant shower of small dust particles coming from the very edge of our solar system or planetary system. Now, that's our planetary system, and that leads us on to other planetary systems, because ever since the very successful RAS mission in the 1980s, we've known that debris disks, disks of dust around other stars, particularly main sequence stars, are quite common. And these debris disks are not stable. If the particle is too small, it will be blown out of the system due to radiation pressure. If it's too large, it will spiral in towards its parent star by the Poynting-Robertson effect. So to have a debris disk that you observe around a main sequence star, it has to be continuously replenished. And the idea is that it's done through intercollisions of small bodies, as we have in our solar system. And this is a really nice part looking at observations of dust excesses in systems that are known to host exoplanets. And so this is effectively the ratio of the flux at 70 microns measured by Spitzer versus what one might expect from the host star alone against age of the system. And although there's kind of a lot of scatter around this plot, one can see generally that as one goes to older systems, the number or the amount, or rather the amount of infrared excess one has as one goes to older systems does get lower, as one might expect, because you simply start running out of objects to collide. Once you've collided two asteroids or trans-Neptunian objects and catastrophically disrupted them, that dust is generated, it won't come back again. And we, of course, have these beautiful resolved images of these debris disk systems. Here's the two most famous, probably. Fomalhaut up here, imaged by both HST on the right and ALMA on the left, and below ALMA images of the dust, the debris disk around Vega. And the important thing is that one can actually estimate masses of material if one makes some assumptions. So generally these are very low mass. We're not talking about large amounts of dust. We're only talking here, for example, in Fomalhaut, in the ring or the belt of dust around Fomalhaut, a total mass of about 0.015 or 1.5% of an Earth mass. But the one interesting thing is that these structures are much larger than we see in our own solar system. In our own solar system, the trans-Neptunian region pretty much extends, the classical belt extends out to about almost 50 astronomical units, and then we do have excited objects beyond that, but it pretty much stops at 50 astronomical units. Whereas here, Fomalhaut begins at about 136 astronomical units, and the Vega belt extends from 70 AU and to at least 150 or 200 astronomical units. Now, it turns out that the extent of these debris disks and these collisional rings of small bodies is probably, it's just a random thing that you can't predict it. Here's a nice plot from a study done from Herschel of how large the effective radius was of the dust disk around stars against solar luminosity. And one might expect that the more luminous the main sequence star, the larger the cloud it came from, perhaps the larger the protoplanetary disk would have been. And yet, certainly if you ignore these two M-dwarf disks down here, and one looks rather at the normal solar mass and high mass stars, one can see it's pretty much a scatter plot, which implies that the size of your debris disk, the size of your planetary system around these stars is not really related to the actual central star. It's really governed by other processes such as collision evolution and planetary perturbations. So I think the nice thing about these collisions in these external systems is that it's telling you about the planetary architecture there. Now that's looking at debris disks around main sequence stars. I think one of the most fascinating areas that I have done nothing about, nothing except read about in the literature with astonishment, has been the identification of small bodies orbiting white dwarfs, stars that are formed, of course, at the end of the main sequence period, or the life of a normal main sequence star. And here's a beautiful set of spectra from HST and VLT published recently of a white dwarf, showing the numerous metal absorption lines in the photosphere of this white dwarf. And of course, white dwarfs in theory are very simple things. They're composed of carbon and oxygen, not a lot else, maybe a bit of hydrogen. And so the question was for many years, where do these elements come from? And it's now understood that this is coming from the accretion of small asteroidal sized objects onto these stars. Now, the idea is that the asteroids are perturbed towards the white dwarf by either planetary perturbations, there will be planets around the white dwarf, or possibly due to effects such as the Yarkovsky effects. Now, I'm cheating here a bit. It's not the asteroid that's going to end up on the star as a single lump, because all of them will become tidally disrupted when they get within the Roche of that white dwarf, which is about 1 solar radius distance from the center of the white dwarf. And they can be tidally disrupted at that point, or they may even be rotationally disrupted earlier on during their infall by the York effect and form a disk or a ring. And it's that disrupted asteroidal material that then accretes onto the white dwarf atmosphere. Now, this is a really nice picture of what happens, and the proof of the pudding comes in spectral energy distributions like this, where we've got the flux against wavelength, and one can see these very bright semi-black body curves here and here. Here, where we see the tail of the spectral energy distribution, the flux on the white dwarf, but then we have this extra infrared excess caused by this material encircling the white dwarf. And again, down here, perhaps this shows it a little bit more clearly. Here we see the white dwarf's spectrum, and then we see this very nice, very large infrared excess. Importantly, if you take a random survey of white dwarfs, roughly 4% show an infrared excess indicative of a circumstellar disk of dust around those white dwarfs. But if you just pick out the white dwarfs that seem to be polluted by heavy elements in their atmospheres, over half of those you see an infrared excess. So this number really just tie together. And the beautiful thing about this is that this allows you to do comparative planetology with our solar system. Because you've got elemental abundances and a relatively simple photosphere of a white dwarf, one can look at the relative abundances of these elements and compare them to the abundance patterns in, for example, the Earth. So on this plot, we have in black the bulk abundance of the Earth, and for this study, the colored symbols show the relative abundances found in those photospheres of those individual stars. And if one looks throughout the literature, the gray bars show previously determined ranges of these abundance fractions. And one can see they pretty much all match very nicely the bulk composition of silicate bodies such as the Earth, with the exception of carbon. One can get very carbon-rich photospheres of white dwarfs and very carbon poor, and we believe this is due to where that material is coming from. If you're carbon rich, you're probably looking at the accretion of volatile rich objects that were originally in the cometary belts or the trans-Neptunian regions around those white dwarfs. So I think this is beautiful, a beautiful work. And you can even have fun with this, because the reason we get into science is to discover things and be excited about it, but also have fun. So one can take the solar system as it is today and say, well, what's going to happen to the sun when it's a white dwarf? And there's been this really nice study by Lee et al. Just published last year, where they took the solar system as it is now, which is a bit of a cheat, put it around the sun just as it becomes undergoes significant mass loss in its red giant stage, and then followed what happened to the main asteroid belt, to the Jupiter Trojans, and to the trans-Neptunian objects from then on. And one can see, for example, up here, that if one looks at the fraction of, sorry, I haven't got my glasses on. Oh, here we go. Yeah, so here we go. Here we have the main, over time, the main belt, the main asteroid belt pretty much survives the red giant stage and the mass loss and production of our protoplanetary nebula. But then over time, over a giga-year or so, it starts becoming depleted. The Jupiter Trojan region really doesn't do very well at all because of the shifting of resonances, particularly with Saturn. Means that the Jupiter Trojans are pretty much lost after a billion years. And then if one looks at the trans-Neptunian region, because of the sweeping through of resonances and the motion and the enlarging of resonances by the giant planets, then one starts losing those after a giga-year as well. But if one then takes those models and say, well, okay, follows them through, how many of these end up on the white dwarf that used to be our sun? Here's the accretion rates that's predicted in this model, going from a million years after the formation of the white dwarf to 10 giga-years. And one can see that it goes up and down depending on which population you're looking at. But you generally look at accretion rates of between 10 to the 6 and 10 to the 7 grams per second, which is equivalent of a single 100-meter asteroid every year falling onto our solar white dwarf. And importantly, in gray here, are estimates of the current accretion rates of studied white dwarfs with polluted atmospheres. And one can see it pretty well matches up. So it looks like our sun is not going to be any way out of the ordinary when it finally moves off the main sequence in about 5 billion years or so. Now, just point out one thing is that one may also have heard of sun-grazing comets coming in to the sun. Oops, oh, that seems to have disappeared. Let me see if we can get that up again. Now, these are real sun grazers, and I've just noticed I've missed a reference here to a large study done by Karen, who's also in the audience, and collaborators. But the important thing is that these comets don't actually hit our sun. We've just been talking about objects hitting our solar white dwarf in about 5 giga-years. But when we look at the orbital distribution of comets in our sun, if we plot the orbital inclination against perihelion distance from the center of the sun, pretty much all of them stay outside the solar photosphere. These are the sun-grazing comets where, because we see them for so little time with solar observatories, these orbital elements are quite uncertain, and it's likely, in fact, that only one object that's so far been discovered, which is a comet in 2007, actually had an orbit that would bring it into the solar photosphere, saying that it probably vaporized before it got there. So that didn't really help. And just to actually add a point to this, although these comets are pretty much vaporized by the sun grazers as they come in, just point out that most near-Earth objects also suffer that same fate. We concentrate on near-Earth asteroids because we're worried about them hitting the Earth. But if one looks at the orbital evolution of these bodies, most of them do not hit the terrestrial planets. Most of them die either being ejected by Jupiter from the solar system or actually impacting the sun. So finally then, just to briefly mention a new class of objects we've had the pleasure and wonder to observe over the past few years, interstellar objects. We've had 2 so far, asteroidal stroke cometary bodies seen entering our solar system. We had Oumuamua in 2017, something that we've been waiting for. We've been waiting for an interstellar object for decades, because we assumed that they must be out there, but you hadn't seen one. And then just like buses, you see one and another one comes along a year later. Here we have interstellar comet to Borisov. Both clearly interstellar. Here's the orbit, or the trajectory, one should say, properly, of Oumuamua, which passed within quarter of an AU of the sun, and the solar gravity really pulled it almost at a right angle to eject it. Borisov came in within 2 AU and moved right further out. Drawing inferences from the population of interstellar objects out there is quite difficult at the moment because they're completely unalike. Oumuamua was relatively inert. In fact, we did not directly detect any outgassing from this object, although precise astrometry of its position later revealed that it had been suffering non-gravitational forces, so there must have been some material coming out of it. Here we have, though, Borisov, which looks like a very standard comet coming into 2 AU apart from its hyperbolic trajectory, saying that its abundances were very peculiar. In fact, this was a very carbon monoxide rich comet, much more carbon monoxide rich than the majority of comets we see in our solar system, and giving us our first look at what we might be able to do in terms of comparative planetology with comets in the future. And one reason to point out that also mentioned Oumuamua, apart from its place in history, is that this object passed within, has an orbit or trajectory that passes within 0.05 AU of the Earth's orbit. And it was large enough so that it was not just the first interstellar object to be discovered, it was the first potentially hazardous interstellar object to be discovered, because it actually passed relatively close to our planet and our orbit. Where these objects come from? Well, we thought we knew that all of these objects would be just planetesimals ejected from their parent stars, generally during the era of giant planet formation. The discovery of Oumuamua set the astronomical world alight, and we have a large number of potential ideas now of how one can form cometary or asteroidal bodies in planetary systems and inject them into interstellar space. And what's wonderful about this is that if we're clever enough to think about these mechanisms, then probably that's what Mother Nature is doing. So it's going to be very interesting over the next few decades trying to work out where the interstellar objects we discover with the Rubin Observatory and other facilities have actually originated. Now, I did mention that there are 2 definite objects that we've found so far. There has been reports of a 3rd one. Siraj and Loeb have looked through the fireball catalogue kept by NASA and found that a fireball observed in January 2014 appeared to enter the Earth's atmosphere at a hyperbolic velocity, i.e. it was not bound to our solar system. Now, looking at those numbers, the numbers seem fine. There is some tension with the fact that out of the thousands of optical fireballs observed by facilities such as the UK Meteor Network and others around the world, they've never seen something like this. So there's something a little bit suspicious here, or a little bit, it needs to be a bit work. There could be biases observational biases happening here, though, at either side. But the interesting thing is if you plot Borisov, Oumuamua, and the presumed size, the center of a few centimeters of this interstellar meteor on, again, a plot, one can see, again, a kind of a power law size distribution, which is pretty similar to what we see on what we expect from our normal solar system populations. But the important thing is that from certainly from Oumuamua and Borisov, one can come up immediately estimate with not 1, but 2 objects, what the interstellar density is of these objects. And if one compares these estimates, which are of order of 10 to the 15 or 2 times 10 to the 15 objects per cubic parsec in the solar neighborhood, they're pretty close to the upper limit that was published in this study, which was out 6 months before the discovery of Oumuamua. So it looks like all the numbers are coming right. The one thing I'd like to point out, though, is that in some discussions, there's been worry that this number density is too large to explain by the normal production rate of planetary bodies in planetary systems. Well, in fact, this is shown by the Oumuamua team just 2 or 3 years ago, that if one takes the uncertain power law distributions of objects formed and ejected out of planetary systems, then although the number density is rather high, one can easily come up with models where one can produce that number of objects out there. So, to summarize, we've got collisional evolution we can see happening now in real time, small bodies in our solar system, with potentially interesting effects if Atlas and Pan-STARRS and everything else don't get their act together. We see inter-asteroidal and intercometary, if you like, collisions occurring not only within our solar system, but in external systems via their debris disks. White dwarf pollutants offer direct measurements of the position of these small bodies by at least their remnants impacting white dwarfs. And interstellar objects do offer a potential method of collecting samples of exoplanetary material without us having to leave the solar system. So this is kind of a wide range of what we might see in terms of small body impacts. So I think to summarize it, I can do no better than to use a quote from a renowned amateur scientist that's stayed with me throughout my career, because Douglas Adams in The Hitchhiker's Guide to Together told me that the secret is to bang the rocks together, guys. Thank you very much.
Thank you very much, Alan, for banging the rocks for us. Can I invite questions both in the hall and online? One here.
The diagram of the lunar impacts was quite worrying in terms of the energy involved and the frequency. And you can't imagine, well, the Earth must have a sort of similar impact because it's roughly in the same part of the solar system.
Well, the important thing about the lunar impact history is, of course, that when we look at the lunar surface today, you know, that's really dominated by the early bombardment history. Yes, that's right. So when one looks at the moon through a telescope binoculars, you see all those lovely craters and large impact basins. Most of those were formed over 3.9 billion years ago, when the solar system was still pretty much being cleared out of the stuff left over from planetary formation. Now, there's clearly been some changes in the impact rates in the inner solar system since then. In fact, there was an interesting study a year or two ago published that implies that there was a sudden jump back up, or by perhaps a factor of 3 or 4, in the impact rate on the lunar surface and thereby proxy on the Earth's surface about 600 million years ago, for reasons that aren't very clear at the moment. Perhaps there'd been a major impact in the main asteroid belt a little bit before then that fed the resonances to drive that material to the inner solar system. But yeah, so the nice thing is that the lunar surface is much older than us in all senses of the word. But importantly, it gives us that insight into what was happening back then, and it's a relatively easy thing to study for us here.
Yep. And
thank you. When they whack that asteroid to try and move its orbit, obviously it wasn't an elastic collision and the thing didn't just stick in it. You got debris coming off. Do we know how much of the momentum was transferred to the more solid blob and how much of it went into the debris, and what difference that made to the orbit?
That's a really good question, and that was actually part of the experiment. That was one of the main goals, to measure that of the DART mission. Now, I can't give you the exact numbers, because again, the papers haven't been published yet, but also because what happened was that we know the momentum of DART when it came in. It was 570 kilometers of spacecraft moving at 6.1 kilometers per second. Now, that momentum went into moving the asteroid, but then we have the extra momentum given by that ejector, and that was the unknown effect that we wanted to measure, or the DART team wanted to measure. And if just the momentum of the spacecraft had moved the asteroid's orbital period around its parent, Didymos, would have been changed by 7 minutes. In fact, the orbital period was changed by 33 minutes. So one can immediately see we've got about 4 times as much momentum transfer as we would have had from the spacecraft alone. But actually working out what happened in that impact is still, of course, it's going to take quite a while to figure out how did that kinetic energy and how did that momentum get spread about between the ejector? What can we find out about that ejector that was dug out of the surface of Dimorphos and so on? And some of that, of course, is going to be worked on from the DART and the Leisure Cube data for certainly the next year or two. But then in 4 years' time, actually less than 4 years' time now, well, that's a good thought. Actually, no, it's exactly 4 years' time. ESA-HERA mission will rendezvous with the asteroid system. And
Okay, thank you.
And that will make those measurements, tell us exactly, precisely what happened.
Right, and of course, that depends on the cohesiveness of the material you're hitting. But the positive side is if you're trying to deflect to stop a collision with Earth, at least you've got smaller fragments hitting as well, if you do the right thing.
Yeah, that's true. I mean, the idea was never to try to completely disrupt this asteroid. DART couldn't do that. I mean, the kinetic energy was much smaller than the binding energy of the asteroid by about an order of magnitude. But what it could do is certainly tell us exactly what happened in that collision. Yes.
Anything online yet?
They're all a bit shy. Need some. They're all a bit shy, Mike. We're waiting for questions.
Come on online. Right, more here. Richard, you know this first.
You talked about collisions with the Earth, the risk of collisions with the Earth. What about the risk of collisions with the mirror of the $10 billion James Webb Space Telescope?
Well, all I can say is try to get your JWST time in the early cycles. I agree. It's interesting that, I mean, the micrometeorite environment in the near-Earth system is not something I work on, but it was interesting that apparently they did not expect such a large impact so early on in the mission. So. Oh yes, absolutely. I mean, even going to the plot where I linked in the lunar impacts to the near-Earth asteroids, you're still looking at objects a few centimeters across there, where, of course, I am assuming that the object that hit the JWST mirror was probably micron size or a few microns. I don't know. To be honest, it's not my field, but yes, get those applications in now.
Mike Robinson.
So one also gets some insight into the collisions between asteroid families from the infrared zodiacal bands, which RAS found.
Mm-hmm.
So different bands can be attributed to different families, collisions between different families. I mean, I think the thing about the TNO dust is very interesting, because perhaps there should be a component somewhere that's due to that.
Well, the interesting thing is that if you look at the simulations imply that the dust content of the solar system is completely dominated by the dust generated in the trans-Neptunian region. 99% of the solar system's dust should be out there beyond Neptune. But it's so cold and it's so faint, and the sky brightness is so low that it has not yet been detected. Which you know, but never say never.
Yeah.
Thank you, Paul Daniels. To what extent do you think the detection of the hazardous near-Earth objects will be hampered by the proliferation of low Earth orbit satellites?
That's a good question. I mean, it's so obviously something that's not just a worry for the asteroidal sky surveys, but for all astronomy. Now, to be honest, I think with our experience on Pan-STARRS, on Atlas, for the next few years, I think things are okay. Of course, there have been many studies about this. The reason being is that low Earth orbits, I mean, first of all, there's no problem in mistaking a low Earth orbiting satellite for a near Earth object generally, because they are traveling much, much faster than the asteroids. Actually, if you've got an asteroid traveling fast, you're in trouble because you've missed it until it's too late. But of course, the real problem is how much of your image every night that you're using to survey is basically contaminated by those satellite tracks, which can be very, very bright, and that saturation can easily bleed into surrounding areas of the chip. And I think it's actually, I think it's going to be a small problem. I'm not sure it's going to be a large problem. The reason being, for example, is that in the near-Earth asteroid game, you always take at least 4 exposures because you want to see that point of light moving in a consistent manner. And unfortunate experience has told us that just having 3 observations sometimes isn't good enough. But if you've got 3 observations, you suspect something, you can go back and check. I think it's going to hurt the transient astrophysical community a lot more, where your object's just not moving. But you may, if you're looking for fast transients and you miss one because there's a satellite trail over it, and you don't get back there with Rubin for another 3 or 4 nights, I think that actually could be more serious than for the near-Earth asteroid surveys. I'm not going to say I hope I'm right, because I don't want it to happen at all.
Yeah. And something the problem of this near-Earth satellites, low orbit satellites, it's something the RAS takes very seriously, and Robert Massiano is doing a lot of work on working with international bodies to frame our response to such problems, and hopefully we can keep you updated and keep them in check. Yes.
Hello, Gail Camp. I just wanted to say thank you. Sorry. Hi. I wanted to say thank you very much for your talk, but I wanted to ask if you could say a few words about Sentry System, which was originally proposed by Rusty Schweikart about for the last 10, 20 years, and how, for example, who is keeping, is it an international effort to keep note of this risk? For example, you mentioned Chelyabinsk. It's another 2 buses because Duende arrived in 24 hours. So that's hinting at levels of risk that may be difficult to manage. Thank you.
So if I'm right, the question was if I could just very briefly explain how this, how the Sentry system or the planetary defense surveys work. So first of all, let me reassure you, it is a completely international system, and it's also completely open in that when an object, a new object or a known object, when it's observed and measured, it's sent to the Central Clearinghouse at the Minor Planet Center over in Harvard. If it's new and it's unknown, it's immediately placed on an open access public website, so any astronomer can go and follow that object up and try to get more observations so that its orbit can be determined. Within 10 minutes, the potential risk from that object has been published on the NASA JPL Scout website. We use Scout as the system we use when we don't have a very good orbit at the moment, and it's pretty good. It really does tell us, if we've got limited amount of telescope time, what are the most important things to follow and track and try to refine the orbits of. Once we know the orbit, then that moves to what's called the Sentry system, where a future impact risk assessment is made, and that's made independently both in Europe and the United States using actually independent algorithms, and those risk pages are also completely open. So I'm afraid to say that if we are in significant danger, the astronomers will know just as quickly as you will know, and just as quickly as the politicians will know.
Thanks, Mike Cruz. is there going to be any significant difference between the impact of a given mass on the Earth's atmosphere, whether it's in a solid form or a pile of rubble? You know, I mean, can you cheer us up at all?
Well, probably not. Not to first order, because one must remember that we've got these objects have a typical impact velocity of 17 kilometers per second or so, which means that you've only got about 5 or 10 seconds for that object to pass from the top of the atmosphere to ground level. And that's really not enough time to disrupt any further that rubble pile object. A rubble pile really goes in. In fact, that question was actually asked going back in time about shoemaking EV9 impacts, because back then we suspected that cometary nuclei are relatively low density, perhaps even perhaps a rubble pile type structure. And so there was a famous paper published a week beforehand saying that, well, yeah, these things are low density, they may be big, but they'll go in, you won't see anything. I'm pretty sure the author of the paper was just really happy to be wrong.
Can I ask a question?
Yes.
One fascinating thing you left hanging, which was this date of, where is it? I've got it. 3rd of May 2029.
Oh, no, Friday the 13th of April.
I've got the date on.
Yeah, well,
I've already invited
well, this is because we'll have a close pass of a famous near-Earth asteroid called Apophis. Why worry? We'll just call it after the god of death. And this actually is a relatively threatening object. When it was first discovered, there was a significant possibility it could hit us sometime in the next decade. We now know that's not going to happen through continued observations, particularly radar studies. But it's going to hang around. It's not going anywhere really, apart from just continuing. It's pretty much in a similar orbit. But yes, well, it will pass the Earth closer to us than the geostationary satellites, and that night it will reach 3rd magnitude as it passes over northern Europe.
The question I really want is there any other in history, has that ever been seen before? An asteroid passing and actually being visible as a naked eye?
Not in recorded history. No. So it's something to look out for. It'll probably be rainy.
Okay, any more questions? Anything online? Okay, well, can I thank Alan for a fascinating talk, really fascinating talk. And you know, we hope you're right, and it's not going to happen in the immediate future, fortunately, except if I could remind everybody that the next monthly A&G open meeting of the Society will be on Friday, the 10th of February. And I remind you that there will be a drinks reception in the RAS Council Room straight after this meeting. And can we thank